There are some modules like the sensors, the ADXL and BMP that are soldered regular for this mount, but there are larger components like the TNC slotted in. This allows us to pull the components out and switch them to boards and do testing easier. And we also chose to use a separate ignition pattern because we wanted to have this work in the event that the igniter is short. So if one of our igniters shorts, the battery just in the dump power from the igniter. And the upstream power from there doesn't have enough left for the TNC, then the mercury will reset. And we don't want that to happen, so there's two completely separate batteries for the ignition and the electronics. And if it shorts out, then after a second it'll cut out and it'll still work for the other thing. For tracking, we have two main systems, GPS and radio finding. GPS is really nice because it'll give us an exact position for us to go to, whereas radio direction finding is great because it's very reliable, it's very simple. All we need is a directional antenna and we can find it. We don't need to worry about GPS reception. I actually designed my own RDF tracker. There are commercial modules out there, but they're expensive. We do a lot of like level 1 and level 2 launches, and we actually do something like this for those launches because we lost some of those rockets. So I built these so we can cheaply make a bunch of them. The versions cost like $60. These cost like $10 plus the batteries for those. So we can make a bunch of these. And we have two of these in the rocket actually. We have one in the upper section in the API bay, and one in the lower section, which is attached to the boat tail. And we also have GPS. We have the primary computer GPS, and we also have a commercial GPS module. The reason we have all these trackers is because last year we had one GPS tracker and it failed, and we were fortunately lucky enough to find our rocket, but we didn't want that to happen again. So we've got plenty of packages.
So now that we have the data from the accelerometer and the barometer, we needed to find some way to combine it. So we turned to a common filter. For those unaware of what a common filter is, it basically takes your sensor measurement data and combines it with the underlying dynamics of your system and to form into to provide you better information of where you are and how fast you're going. That's better than either of the two alone. And the pros of this is we get better estimation of where we are, how fast we're going, and we can tell apogee a little bit better. The cons add some complexity to the rocket, and if you're aware of common filters, they are linear. There are ways to make them to deal with nonlinear systems, but rockets are inherently nonlinear to drag. So, if you're familiar with common filters, on the left we have, I'm going to try to use the laser pointer. The nonlinearities come from the drag, which comes from the whole velocity square term. But as we're closing in on apogee, the velocity drops to very close to 0. And at that point, we can discard the drag term and use it, the dynamics of the system become linear. So we can use the common filter and just plug in dynamics. For those of you unfamiliar with what a common filter does, on the right side there is basically, this is some raw accelerometer data. It's very noisy, a little bit of a signal in the noise, but it's really noisy. On the lower graph, it's still the raw accelerometer data, and the red is some filtered data. This is not the exact same gains that we use on our common filter, but this was just chosen to highlight how the filter is smoothing out the data, providing us more basically readable data we can deal with. So for testing the system, as with any new system, it needs a lot of. So the way we test is, a member of our club has a large quadcopter. We mounted a build flight computer on it, and then we flew it on a quasi-ballistic launch simulation. Basically, a quadcopter went up as fast as it could, and then we let it come down. And so to simulate a launch and then slow recovery. Now, I'm going to highlight 3 main tests. As we were iterating on our design, we had more tests than this, but these are the 3 important ones. There's functionality tests. But for the first test, we had some late actions. You needed still, one part of building a common filter is tuning that common filter. You needed how much error is in the noise, and how much error is in the measurement noise, as well as how much error is in the noise. So that's what we were using the real world testing for. The second test we had, we weren't able, our flight computer didn't work because the accelerometer broke. So we needed to go through and design it so that way the accelerometer is at less risk of breaking. And then for test 3, we had an accurate and low apogee detection. Now, earlier I said that the common filter comes raw measurement data with the dynamics, the underlying dynamics of the system. And you might be asking yourself, isn't a quadcopter a system than a rocket? And yes, they are. The drag on a quadcopter is much higher than that on a rocket, the coefficient of drag. But the way this would manifest itself in when we're tuning the filter is it would mean we have a lot of uncertainty in our model, and that would just make us rely on measurements. So we're building a more conservative, our common filter trusts measurements more than trusts the model. So it still gets some of the benefit of the smoothing, but we're conservatively leaning towards the measurements themselves. So in conclusion, we have a working flight computer. We use a filter for apogee detection. We have data log, live telemetry, and GPS and RDF tracking. Now, what about that portion, the video? Did we get it working? Well, everything works. I haven't been able to launch the video module, so come and find me tomorrow at lunch, and I'll let you know whether that part works or not.
All right, and in future, we want to make it all better. We want to make it cheaper, smaller, and more power efficient. Also, we're using 2 separate batteries for the ignition of electronics. What we could do is combine that into one battery and use a capacitor or something so that if the igniter does short, we can still keep the electronics running without needing a completely separate battery. And that would make things obviously cheaper and simpler. And also, we want to design our own radio. This year we're using an XP. However, as you may have noticed on that RDF tracker that I designed, there's a little radio chip on there called the CC1150 on the right. And we can use something like that. It's a PAX radio, and we can send commands and transmit data to it. The XP actually has a chip like that on there, along with the microcontroller and stuff, which basically just makes everything a little easier to use. But if we access the chip directly, then we should be able to get better throughput, lower latency, and and we can also make it so that it transmits with higher power level, because I'm an amateur radio operator, so I can use higher levels and different bands and stuff than what XP is really designed for, since it's designed an ISM band on licensed device.
And before we open it up to questions, I just want to answer one question that was asked earlier. When the question was whether we are using any raw altimeter data for lockout, basically, so that we don't deploy too early. We're not using any raw barometer data for that purpose. It's a good idea, and I can look at it next year for the next iteration of the design. So with that, are there any questions?
As I asked that question, now that you told me you're conservative common filter. Okay. Can you go back to your first slide, the 4 goals again? And then, are all 4 of those functions on those? They're not all the little cards you showed up there.
Oh,
CCA that carries those.
I know
those
this.
sections were.
This is what you saw on the flight computer. This is just the tracker. So this gets acted up in conjunction with this. Yeah.
They're 2 separate.
And does your flight computer and your tracker that are in favors too?
Yeah, so
They
there's
stay in batteries?
they have separate batteries. There are actually 4 in total. There's 2 GPS one in the avionics bay. There's the one on this flight computer, and then there's one as the commercial module that's separate with its own battery and everything. Then there's one in the RDF tracker, which is also completely separate, also in the avionics bay, and then there's another RDF tracker in the tail section.
Redundancy is on the domain.
That's good. And you said you wanted to maybe change out the battery that runs your flight computer. How did you come in with your entire battery? Don't worry about that. It's actually, I think, better to have them separate.
Can you manage for how much money you got this sort of setup?
So the teensy is like $20-30. Then the GPS is probably another $40. The XP is $40. The accelerometer was a lot more expensive than I thought. It ended up being like $8 each, and we're not going to talk about that. The VOP280 is like $1 maybe, and there's a bunch of passive components. The actual PCB itself, we bought it in a wash car, and it cost
$5 per square inch.
yeah,
$30
total
for
like
three.
$30. Plus there's an extra charge.
Which components or which functions again? Repeat that.
So that XP has a radio.
I know, through the middle.
This one's the GPS, I think. This is the accelerometer and this is the barometer.
Oh, I meant up above your designations, which were which?
This is the barometer, accelerometer, radio, and GPS.
Okay.
You guys just gone to the, all those up some?
The way we have it right now is off.
And this runs part of your deployment mechanism, but is that a cost backup somewhere else?
Yes.
How does RDS tracking work? Do those modules you show, are they just beacons that are?
So basically, every 10 seconds for 2 seconds, it'll just play a tone at a certain frequency, and you get a directional antenna, and you can find it that way. We actually made a TDOA antenna, time difference of arrival, so it's actually got 2 antennas, and then there's a timer, which basically switches between those antennas really fast. And what happens is, if both of those antennas are exactly the same distance from the transmitter, then you hear the tone in your radio. But if you angle it so that one of them will be closer, then that switching will create another tone. So you'll hear some noise when you twist it. So you want to line them up, and then once you've got it, so that you're hearing it, so you know that the rocket is either straight ahead or straight behind you. Then if you do 2 things, of course. What's that? Oh, so MissileWorks in particular has their own computer which uses these modules. I also looked into these whole bunch of other systems. I chose because of their range, because they were on another flight computer, so I didn't work. I chose them because they were really easy to use. They just expose a serial port basically, and you just send data down that serial port, and the XP things out and gets it to the other end. You don't really have to worry about setting individual packets and stuff. The downside of that is there's a little bit of latency, like maybe 500 milliseconds or something. If you made your own chip, you could send it out if you know it would get there a lot quicker.
Did you do any range tests for the RFP tracker?
We walked around campus and there's the RDF. Yeah, we also did the same thing. So one of the other team members played around campus basically, and I got it.
So how big is this?
Pretty easy,
About 20-minute walk times, and it's a nice long slender campus.
What's, I'm curious, you're obviously putting both trackers on your pieces.
Yeah.
Are they both, was it ISM you said?
So RDF trackers, I'm running them under amateur rules, and then the GPS stuff is using XP, so it's under ISM rules.
And all of you get your amateur radio license or just your advisor?
I have. Anything else? Thanks, guys.
What's our next thought? Yeah, they're in the back too, yeah. So let's listen, Rice, and, before I do, real quick. Yeah, certainly want to hit Rice and Victoria. Since they're the two guys, then we had BYU and Turkish schools at all 13.
Power one, got it.
One mark, one up top.
All right, yeah.
that's just a preview of what we talked about today. I know earlier, we wanted to take this here, on the appetite model. It is basically that we run, it is what we run, no, run the application of our goal, of our leadership, is to bring that traffic to them. Okay? For us, it's really a great time to go to. I think we're going to 12 years. I know that's okay. But it's not about running a big presentation for our people here. I think it's pointing out, but the big thing about it is so wherever they go, coming out with their big workers, like, starting, we want to focus on, but,
Okay, so you might be using this microphone, which means you can rest your hand on the podium, which is nice, because then you don't have to worry about amplifying. I would go not podium, I would go like, I think your best.
Testing. Is this like good?
Then you can see us, and maybe get all sort of.
Is it good volume?
Yeah.
Okay.
Hold on.
Sally sold seashells by the seashore.
I don't know, well, the lid is.
yeah, I
Oh, we have a clicker. Yeah, there probably is a laptop that sits right here, that they took during lunch, because they didn't want to slow them. Right?
Can we grab our laptop just in case?
No, because I asked him, I said, is there a laptop available on the laptop box?
Our club is like a jigsaw puzzle. We stick things in other things.
Hello? Is that clear? Is that about it? So on the right here, you can see a blank screen. So that, okay, so that's actually a very good point. If you turn, you're no longer talking to the mic, right? So you have to like stay like that, or at least like go, I don't know, like, you have to be cognizant of when you turn your head, your volume will drastically drop.
Right now, it's.
One out like that?
Yeah.
Oh, yeah. Okay. Oh, when I'm talking? Let me see what makes sense. Yeah. Let me just take it off. Walk. Okay, I'm standing here talking. You stand. I don't know, we could step down from the stage if we want to be like really out of it. But I think, here, wait, Renee, swap. You go up there, so let's see what it looks like having two people. Yeah. So, yeah, you go to the podium and then. Yeah, I think you stand.
What if you stand here on this side?
Because it's weird having you stand back by the wall, like you do that flat.
But I mean, he's gonna talk too, though, isn't he?
Yeah, you didn't walk forward flat, right?
Far away, but.
Yeah, but I don't want it to be like distracting having the same
Oh,
person there
okay.
and not talking.
That's true, that's true.
I could just like walk up right before we switch.
Yeah, like there's honestly like, I don't think people are gonna be watching us that much. You don't want to be, I think you're better off invisible. Like you don't want to be right here because then you're a distraction.
No, that's
So
true.
if we,
Actually, that's not what I do, like, just put it to the side back,
or even like, if you just stand here up against the wall, no one's gonna care. Like, if you're.
yeah, like, focus on this conversation.
Yes, we want to get out of the way. So if you, and then I think what you do is, when when I get to the firewall 2 slide, you start walking up. Okay. And then you can stay behind me for like a second and like, you know, say it over, and then I'll turn and walk out. Okay. Well, this is great. We're right there. So yeah, I'll be talking about the slide.
Yes.
Yes.
What's the topic?
We're talking about having removable motor mount and fin assemblies, so like you can reuse your body tubes and not glue everything together.
Right. Okay. We got to decide before we go to.
Yeah.
We didn't put up the titles.
Oh, that's unfortunate.
Yeah.
Get the pictures of this.
I hope like 20 people here. Yeah. I don't want a full house. I don't need a full house. I don't need that. My ego doesn't need that. My ego already got yeah, so when I'm talking about firewall 2, you can quietly just start walking up, and if you time it well, I'll just be like, now, and you could like stand like right there while I finish up in that Raven, and then I'll turn this way. You go to the podium and out, and we'll do the same thing when you get to the launch test. I'll come back up, stand here. No, that time, go just to the back, I think. And then you're going to come forward for the questions.
Well, I don't think we should stand, actually, I don't think, we should stand all the way back there, because the stairs is going to be starting.
So you want to just,
I think you should just stand up there and
just stand here?
yeah. I think that's fine.
Yeah. So then you're out of the way while
Yeah.
the person talks.
Exactly.
Okay. And then watch when I do it, I'll probably just stand here and like, I'll maybe be just barely use like this, right? Keep me here, and I'll be watching you, but don't be like all over the place, and like make sure your expression is not. It can be passive. That was a big thing when I used to make drums. I used to look angry while I the other smile. No one's watching me. Okay, so maybe I can use it. But I think everything's probably. I just.
Can you grab the laptop? Just in case.
Yeah, go grab my laptop. Yours coming in a second. I'll text you if you don't need it.
Okay, just don't let it.
Yeah, I'll watch.
It's just us, huh?
Yep.
The other guys are inbound. So you take 10 seconds to time.
Where are you guys from?
Dayton, Ohio.
Originally from Southern California, but if you saw Arizona, for us 25 years.
I'm from New Jersey.
How did I from New Jersey go over to Texas?
So, what I always say is I fell in love with rice and it just happened to be in Texas. I didn't look too good in Texas, but I do like it. So,
Is rice have a religious affiliation?
no, it's completely non-religious.
That is not like people are not, it's not like Baylor or anything like that. Baylor is a Baptist school. So,
We don't buy. Yeah, no, it's just not.
I don't know, okay. No religious affiliation. It's old, I mean, this is the old school in Texas.
It was founded in 1912,
Oh,
1911, so it's not that.
Not that old.
Yeah, it just had its centennial.
I thought it was like a week.
Yeah, I'm sure A&M has its feet like that before.
And I think A&M was an internet college, they probably in the 1870s, 1880s.
Do you guys, what do you guys choose for like
I just retired from the Air Force, and they have Air Force Service like authority. I worked in hypersonic propulsion, basically, high-speed fuel for rockets, transmitters, all hydrocarbons. Non-consultant, but I have a big, liquid testing on my own, new space round, and that died. And every other new space company from 1985 until roughly the late 90s, 100% of the new space companies died.
Orbital was the first new space company, because they did it. They shouldn't have survived, but they did. They started in the late 70s.
Yeah, Orbital was a little different then. They were.
When did ULA start? That was.
What was the word?
Lockheed and Company.
Right, yeah.
Okay, you start.
Well, so the issue is we went to grab one of our laptops. We were told that they had a laptop that was plugged into the presentation, but I don't see it. So we're getting our own laptop to use.
Is it in that?
Yeah, it's on its way.
Okay.
Yeah, sorry about that.
Usually set up.
So you think he's out there? Sorry.
The great group of engineers, you can talk about your slides, so
I can do it.
why don't you talk about your slides?
So we're not allowed to bring our prop stuff. If we could bring them.
No, I know, just talk about the slides and that's the,
Which slides?
the slides because they have any computers.
Yeah.
Well, they can't, you can't hook up.
Yeah, I don't think it's gonna have to wait for.
No, you need this one, those two, yeah.
Yeah, we need a.
That's the one.
I'll tell you what, if you want, you can sit here and go full screen and just sit right there. That's, I mean, really, you only got so much time.
Yeah.
Let's spread out some of the.
Yeah. We're only 4 minutes behind. We're just coming out of lunch.
Yeah, there's a
What?
They're all the countries go to the second.
Yeah, I'm sorry. We put a lot of time into this.
I believe you, I agree.
Yes. It's about removal motor assembly. Sorry.
You see what's out there? Go get back here.
Liver.
Oh, no, that's, yeah.
Well, hello. My name is Jeremy. This is Raymond. We're going to be giving a presentation. We don't. There was supposed to be a laptop here. I don't know. It'll happen. We're trying our best. We'll just do some intros. We go to Rice University.
I guess we're on hold.
We're going to give a couple minutes.
Okay.
Cliff usually brings his own laptop, which is old enough to have a meeting.
Okay.
And if not, we'll gather around.
We gather around the computers for me.
Okay. Yeah, we'll do it. Yeah, we're students from Rice University. I can give you a brief intro about our clubs, but I have to at the same time do a presentation. Our club is called Rice Eclipse. We started about 4 years ago down in Houston, Texas at Rice University. We primarily work on making hybrid engines. So we have a 50-pound hybrid, 50-pound plus hybrid engine. I'll show you a picture of once we get this.
No, okay, we're just rolling with you. And when you guys get here,
Yeah, so I'll do our intro stuff, and then hopefully we have the slides so we can show the thing that matters. So we're a club down at Rice. This is our first year competing in Spaceport America Cup, so we've taken a very conservative approach to the competition this year. Our primary goals when we started were rolling our own carbon fiber tubes and having our motor tube and fin assemblies detachable. We worked really hard on making that. What we found in the past was that our rockets were put together similar to jigsaw puzzles. And if you ever put the jigsaw puzzle, you know when you get to the end of it, it's incredibly frustrating if you lose a piece because there's no way to finish the puzzle, and now you just have a useless puzzle that's missing a piece. The same goes for our rockets. Everything was glued together, so when a fin would break, or maybe we need to change a motor tube size or length, or change our body tube, you had to build a whole new rocket from scratch, even if you're only changing one feature of one component. And this was really inefficient for us. So our goal was to go forward and be able to create a modular rocket where you can replace components and reuse them to save cost. The other limitation we were seeing was that glue has an upper threshold to its strength, right? You can only add so much glue before the glue is going to break and won't sustain force. So we wanted to move on to bolted connections rather than sustaining the same glue ones. Yeah, well, I'll talk about our rocket as a whole. So our rocket is called Noctua. You'll hear that a lot through the presentation. Noctua is the constellation of an owl, and Rice's mascot is an owl, so we thought that was a fitting name for our rocket. We're competing.
We're running from this one here?
Okay, yeah, we don't have a laptop.
Oh, you guys don't have a laptop?
No. Yeah.
Yeah, let me just go grab the adapter from the BJ, just the screens are linked.
Yeah, that would be great. Yeah, we can show you. Yeah, absolutely.
Just go grab the adapter from my bag.
Okay. So our rocket is called Noctua. We're competing in the 10,000-foot category, Cox motor. So we're launching on an L1170 motor with launching rocket we've flown. We've never launched 2.5 feet higher than 3,600 feet. So we're excited to see how this goes and see what we can do. I can do the presentation or I can ramble. So I'll just skip all these. So in the past, we kind of played around with bolted connections and removing oxy from our rockets. So what we did was we started a project we called Firebolt. Firebolt because bolts were holding it together, and Firebolt because we love Harry Potter, if you've heard of that. And we started by just mounting 3D print brackets on the outside of our rocket body. So we had these brackets where the fins could slot into bracket, and you could bolt all of the brackets externally to the rocket. And it worked, it held the fins on, and you could mount the motor through there, so everything was removable, so it achieved its goal. However, because we had those fin brackets on the outside, as soon as the rocket motor cut off and we were coasting, it tumbled out of control because there was so much drag down the base of the rocket from the external hardware. So from that, then we moved to a new Firebolt, Firebolt 2, that was internal. So we 3D printed a fin can that had slots for the fins internally, and we could bolt all that in place. It worked fairly well, but what we discovered was there's another limit to your 3D printed piece strength. We quickly found, as our eyeball ripped out of the 3D printed part, that plastic definitely doesn't have the strength of fiberglass, even if you 100% infill. So we knew that 3D printed parts are great, they are fantastic manufacturing capabilities, but you can't rely on them for the overall strength and complete support of the rocket. That's my section. Yeah, we have. We'll go back through pictures very briefly, and then we'll go. I think I can show you better with the picture, but you have a bunch of basically an extra 3D printed block at the base of your rocket as a wider cylinder, and once the rocket wasn't powered, the stability was thrown off because our open rocket sim didn't account for all that drag, and we basically I think it was also possible the fins were too small. That was also a contributing factor. The fins were very tiny, which I can show you. So I don't think we had a very stable platform. Yeah. Well, I think the 3D printed part took up a lot of the fins area. So the fins were smaller than we might have assumed they were. Are we ready to get this form up? Or do you have a presentation I have on the class?
Yeah.
Yeah. Sorry about this, everyone. Any questions about the first hire, either one, about the club or rocket? So our funding, we get some through Rice. The Rice Engineering Alumni has been very helpful, along with some other parts of Rice, Mechanical Engineering Department, Makerspace. And then we solicit funds from companies, and we have to slide.
So we have other Ukrainian support, in-kind support.
Yes, we get a lot of, we've gotten like valves from a company where they don't cost money, but they donate spare valves. We've gotten some, I think we had some avionics components donated. So yeah, sometimes we get support that way. And then also some mentorship, which is always fantastic. It's in, we had it in
Laptop would be a solution, I suppose.
Yeah, let me see a portion. Oh, I can live with that. Can I click from? Oh, I can control. Don't look pictures of it. Dark. Everyone kind of see it. Moderate. Yeah, maybe we turn the lights off, then maybe let's see. No, that's not easy.
No, that's his audio.
Because my system told me.
He's got it.
Here's one. Get all that. Yeah, so we're gonna run. Oh, I skipped all that. So when we started this project, we decided on several constraints. Basically, things that if we fulfill this with the design, we would know that our design would fail. First of all, we wanted it to be removable. The primary goal of the project, we wanted to be able to remove the motor mount fins completely from the body tube and reuse it. The second thing was to have it still be secure and stable. If the motor isn't retained well, or if we don't have a correct motor holding, then this isn't successful either. And then finally, it needs to be aerodynamic. We learned that a non-aerodynamic rocket doesn't work very well, and if this creates an incredible drag or causes the rocket to be unstable, it's not helping design. There will be several objectives. These were things we wanted to achieve as well as possible to optimize performance. The thing was we wanted to be easy to remove and easy to put together. We would be putting it together several times over and over and swapping out different hardware. So we wanted this to be an easy, painless process. Second was we wanted to be lightweight. If it drastically increases the weight of the rocket, then it's going to destroy performance, and that's not helpful either. And finally, cost. The whole of this was to save cost on carbon fiber and save cost on other components. So if it ends up costing more than without it, then that's not helping the side. So I mentioned one up in the upper left there, you can kind of see one of those large bulky fingers. It kind of ruins the airflow a bit and takes up part of the area. So yeah, it comes out, and we talk about that. Here, blurry, not visible. There's a fin can in the upper. That's internal on the rocket, and that holds all of those components internally, so that works well. But this is a rocket where the eyeball trick back. So as a brief glance at a solution that you have a motor mount on the left-hand side here, and that can slide up into the carbon fiber tube. It's too dark to see, but there are slits cut to the base of that carbon fiber tube, so the fins can slide all the way up from the bottom, and then that bottom cap seal the bottom of the slits, so you don't have an odd aerodynamic vacuum into the rocket. With that, I'm going to give Raymond a chance to work with this projector and tell you guys about the rest of it.
Okay. Thank you, Jeremy. Moving on to the fireball rockets that we made, came our first iteration of the Noctua rockets. The difference between Noctua and all our rockets previously is the fact that we utilized a handmade carbon fiber body tube as opposed to cardboard body tubes we used in the past. Furthermore, this specific iteration of Noxua uses no creative components, and it builds off of the 5-volt prototypes, and all the components are internal. The biggest weakness of the Firebolt rocket was the fact, as Jeremy said, that the 3D printed pieces were not structurally sound, and that will rip right out. So we replaced important structural components with the material, namely these fiberglass centering rings. In the top left, you can not really, no. We have these fiberglass centering rings that are bolted inside the carbon fiber tube, and these hold the motor mounts in place and provide the structural stability we need. For this specific iteration, we utilized wooden fins that were really epoxied onto the carbon fiber body tube to create this permanent connection, and we test this in around mid-March or so. The limitations with this first iteration were that because of the permanent motor mount system, we couldn't remove the fins or change the motor, which is what we needed to do in order to test different fins and motors for use in the competition, as wooden fins are obviously not the best. So that led to the design of our current motor mount assembly. It contains a completely removable motor tube fin. It contains, the fins are fiberglass and reinforced an outer layer of carbon fiber, and it contains the fiberglass centering rings from the first iteration. They proved to be structurally strong from our previous test lab. It also contains 3D printed components for added support and aerodynamic stability. So the diagram on the screen shows our key components in this detachable mechanism. In the purple, you see our fiberglass fins coated with an outer layer of carbon fiber. In the green and the red are 3D printed pieces, the bottom cap and the fin support ring, which I'll detail later in the presentation. In the gold, that long piece is the carbon rotor tube, which houses the motor we plan on using for competition. And there are 3 centering rings spaced equally along the motor tube, the fiberglass end.
I just dimensions.
Go forward.
Yeah, I just want to make sure that they're fine.
Okay. So each of these fiberglass centering rings, there are 3 of them basically on the motor tube, and each ring is epoxy normal to 2. Each one contains 6 tapped holes in which the bolts connect to in order to attach the motor tube assembly with the carbon fiber body tube. One hole on each of the centering ring is used for railgun attachments, which attach to the rail guide. In terms of construction, we created these centering rings out of a plate of commercially purchased 1/4-inch thick fiberglass, and we milled it and tapped the holes using resources found at rice reservoirs. So the key idea behind our fit motor mount mechanism is that we have opens, we epoxy the fins onto the motor mount rather than the body tube, and we create open slot ends on the carbon fiber body tube. This allows the assembly to slide in and out of the carbon fiber tube, thus allowing the whole system to be separated from the body tube and allowing the body tube to be reusable. The limitations with this we found, however, are that because the fins are epoxy only onto this compromises the structural integrity of our rocket, causing more failure and such. And the open slotted body tube ends also disrupt the airframe, thus decreasing our aerodynamics. So to combat these issues, we created 2 different 3D components. We have our bottom, which is a 3D printed disc with 4 protrusions sticking out that can slide onto bottom open-ended slots. If you could see the picture, it slides at the bottom end and is bolted onto the bottom, thus closing the open slots and completing the airframe, greatly improving the aerodynamics of our rocket. We also have a spin support, which lies in between the carbon fiber tube and the motor tube, and onto it. It adds structural stability, so the entire assembly, the fiberglass fins, the fin support ring, and the motor tube all epoxy together, thus helping fin flutter and adding extra structural support. So after creating our we decided to test how easy it was to mount and dismount our system. So for testing, we wrote a set of instructions and gave it to 3 members of our club not associated with this project. Timed how long it took them to assemble or disassemble the rocket assembly not including time to read the instructions. And you can't really see the average clock under approximately 7.5 minutes to assemble the motor mount assembly and 6.5 minutes to disassemble it. In terms of our weight and cost objectives, our motor mount is 2.5 pounds. We wanted it to be under 2 pounds. However, this extra added weight can be justified because the extra mass adds structural stability, such as the fin support ring. That is mass that we but needed to create a more sound structure. We also wanted each motor assembly to be less than $250 to manufacture with the cost of materials. It was only $100. So with the first and second Noctua prototypes, the first one, which included the fiberglass engine rings but not the detachable motor system, we flew that in mid-March motor, and the purpose of this test was to verify the fiberglass engine rings as well as the carbon fiber body, as it was the first time we ever used one. During this prototype, our rocket's recovery system actually failed, and after reaching altitude, to ground. But this provided very valuable information, as when we recovered, we found that the carbon fiber bodies had not been damaged at all whatsoever, despite that, and which validated our claims of the strength of the carbon fiber bodies. In early May, we tested the second Noctua prototype, included the detachable fin mechanism. And the purpose was to verify all our systems for the competition. We flew it on a K motor. We wanted to test the structural stability of attachment fin assembly. We wanted to make sure our customers, and luckily the recovery system did this time. So to talk about the successes and limitations of the project, I'll hand it over to Jack.
So, really briefly, I want to. So as far as successes go, we're very happy to remove the motor mount assembly since that was the whole target goal. It's fairly quick to mount as a testing. It's also structurally secure. We've launched a J and a K. And formulations we've done on full strength. We're fairly confident it will survive with the L. And then it's airlink. We kept everything internal, and we don't have any major disruptions to the airflow. Limitations, however, the fins are only attached down to the body tube, so that present a decrease in the fin attachment. We tried to overcome that as best we could, but that allowed glue weight and plastic weight, so that added to the weight of the project. It requires assignment. We have CNC milled to be able to create something like this, but if you don't have that available, you can't mill those fin slots or drill those holes precisely. And then we have thicker fins. Thinner fins would have been nicer to save weight, and it would be nice to be able to remove them from the motor tube and not have them glued in place as well. So in the future, we'd like to redesign to have detachable fins so we can pull them off of that motor tube, and then also have it for varying fin thickness. So if you decide to have 1/8 inch thick or layer more carbon fiber to butter, we want to have that variability. So we're going to launch tomorrow, and in the fall we want to launch it again with a different motor mount, different fin shape, just to prove that this system can work for different motor mounts and fins. If we can show our sponsors and thank them for all their help throughout the year, both monetarily and also just by advising us, helping us create this. Finally, I want to leave you with this. I would like to show you a picture of our complete rocket, but it's very blurry. But we're very happy with what we've produced. We think it's going to work very well tomorrow, and I'd be happy to answer any other questions the last couple of minutes we have. I'm sorry. Any questions or answers?
Well, I'm going to stop for a second. These are new coins we're giving out. They're cookie chips, and they were given out on the spot things. So I want to give these to you guys for congratulations.
Appreciate it.
Being adaptable. One thing as an engineer is you're going to take away your slides and make you sit on your hands and talk about your project. You guys did that very well. So congratulations.
I'll tell you something about the real world. I told couldn't present it. As a joke, I give them I give them the box. If they had all failed, we're going to have to roll these things. And it actually did the real work, put out the charts. And we just kept up and presented your stuff and we're done. A few laughed at it and
We're good. Yeah. Actually, if you can fly tomorrow morning, you guys, better early.
Yeah. Oh, one question. You said you tested with smaller motors in it. Was it the same motor mounted to and
Yes, so
you have to do nothing inside that the whole time?
So for the J motor, it's a great question. So he's asking whether we had to have motor mounts for different sized motors. The J motor was smaller, I believe it was a 54 4 on the J. So we created an adapter that into the motor tube to adapt for the difference in size. The motor was the same size, 75 millimeter as the motor, so I have an adapter for that. But it was shorter, so we accounted for that as a black power charge.
Yeah, I have a question. So I have a section of the base there, the 3D printing. Do you know what a characteristic of the strength is?
Yeah, so the question was, how strong is the 3D printed piece of the base of our I do not know the exact strength numbers. We didn't worry about that too much, which sounds bad, but because it's not a structural thing, it's not holding anything together. At the base of our rocket, so there's, at the base down below that fin support ring, there's an aluminum ring that's going to bolt in below that. So that's what's actually retaining the motor. That fin support ring is not structural or holding anything in place. It's purely to seal the holes created by having the fin cells. So have a rigid metal retaining ring in place.
Well, you mentioned the portion below the bigger and thin. Now, you have the spots of them, basically. You get that the same, or you try to make that a little narrower too.
So the question, like changing fin thickness. When we started this, we've only really done superficial flights with wooden fins, and we'd always use 1/4 inch thick wood, right? Thinking it through very much, we arrived at 1/4 inch fiberglass, but we wanted to try layering carbon fiber onto them. That added too much thickness. So ideally, we would move to an 1/8 inch fin, still layering carbon fiber. I'm dealing with the varying thickness. We're picturing either a 3D printed slot, or maybe we machine some kind of slot that will fill the gap inside of the fin, so you can have a wider fin slot cut with carbon fiber. But if you put a thinner fin in there, you don't have a gap. So
I guess I recall when the slots, there's 3 flaps.
there are 4.
That's not load bearing that way. Some other structure.
Yeah, so the load bearing is we have 3 centering rings, and the 2 further up have all of their bolts, kind of like the motor presses against there, and then the wheel centering ring, which is in the section you're talking about that has maybe a little bit of flutter. Centering ring holds all of that together.
One thing I really like the design was, I think like leaving those a little loose.
Yeah.
So
That's why we have bolts from each one into the centering ring to make sure that there's no those pieces of carbon fiber. Yeah. So the question referring to in the slots. Well, in the slots of the basic carbon fiber, it creates basically 4 rectangles that can be easily bent in the rocket. So to combat that, each of those rectangles is going in through the fiberglass centering ring, so it can't flex at all. And then we also use those sets called our rail lines for guiding the launcher using larger bolts. So it's not just, we used to just put a bolt through the side of a rocket and then flops around.
Any other questions?
Appreciate it. Yeah, no problem. Have a good rest of your day, and good luck to the teams that are here with their rockets as well.
You guys want to read it more? Let's meet the one of the judges' rooms, and then we'll go and finish up the rest of the meeting. Okay? You guys are one. You get something more to eat, I guess it's there till 1.
Yeah. All right, well, hello everyone. My name is Jonathan Lassad, I'm captain of the Field Rocket Team, also the lead of the Aerostructure Sub-Team. And today I'm talking about how we use resin infusion to manufacture our composite airframes. So just a quick overview of the presentation. We'll introduce and motivate the topic. So talk about the materials we used and the type of characterization we did, by how we actually went about implementing this manufacturing technique for our own purposes. And finally, take a look at the quality of the parts that we produce. Now, before I get into anything about resin infusion, the first thing I want to kind of motivate is the idea of process. And perhaps this is more obvious to some of us here than others, but the properties we get out of the composite is very closely related to how we process it. And because of that, there's uncertainty. As such, engineers who do design composites apply knockdown factors. And you can see some of this graph right over here. So they'll take a relative property, let's say strength, and reduce it. And some of these knockdown factors are unavoidable. Dealing with things like material over time, temperature variations, and environmental changes, which are also going to affect costs. But the biggest knockdown factor, 40%, comes from manufacturing. So what we're doing here is we're trying to design a processing technique in such a way that we can minimize that knockdown factor. And if we do that, we can really start to take full advantage of the properties. Now, there's all kinds of ways to process, and the way we're focusing on today is vacuum-assisted resin diffusion, or I'm just going to refer to it as infusion. And here we have our setup of what an infusion process looks like for just a flat plate. On the right, you have your reservoir. This is where you supply your resin from and how you're going to draw in your components. And then right in the middle, you have your actual setup. So first thing, you have your tool. This can be usually in mold, or it can also just be a flat plate, which you're infusing it. On top of that tool, you have your preform. The preform in an infusion is going to be a direct fiberglass, carbon fiber, Kevlar. On top of that, we'll have the consumables. So on the left side here, you can see we have our solid inlet, which is where the resin's going to come in. Start with the outlet, which goes to the vacuum pump, that's it. And everything's underneath the vacuum pump. Finally, just on the right side, you have your vacuum catch pot, vacuum pump, which you need to move the air, and the catch pot, which you need to prevent any resin from inside of your vacuum pump. And to bring this processing technique down, we really have 3 steps. First things first, you lay up your preform that's going to be part you're making, and you're going to do this with dry fat, right? You put it under a vacuum bag, you pull back, make sure there aren't any leaks in your vacuum bag. And then, once you're ready to decide, you open up the inlet line from the reservoir, and the resin starts to travel through. You can see here outside, where that's more dark or it's black, that's where the resin actually is. And on the right side, where it's more lighter, that's where the resin hasn't made yet. And right at the boundary is the flow front. On the flow front that we're going to want to control, there's nothing that's going to be worse than if our flow front's kind of diagonal, and the resin travels through here, it doesn't hit the bottom, right? You want to control that as much as possible. Now, once the preform has been fully impregnated, you leave this thing under vacuum pressure and you cure it and fire. And that's going to depend on the resin system that you're using. Now, why do we want to use this as opposed to different manufacturing techniques? So, we decided that a good way to come up with this is just to compare a few of the different manufacturing techniques that we see here in the competition. And the first one is wet lay. This is seen all the time, when somebody applies by hand to the carbon fiber or to the fiberglass. And it does have this effect, it's that the cost of material is low, you don't require a lot of infrastructure, it's just somebody needing to apply the tool and the materials. But the problem with this is that you're relying ultimately on the skill of an operator to apply that resin. And as the quality consistency and variation times, which is reduced. Now on the flip side, we have prepreg, very high performance form of composite where the fabric comes with the resin already inside. And it has great advantages to it as well, right? You get great mechanical properties from this, and you can get some pretty decent quality consistency as well, if you are depending on the part you're making. The problem with prepreg though, and the thing that's difficult, especially for a student design team, is that the materials are quite high. I was looking at the website the other day, it's 2.5 times difference between SRAD versus SRAD, and as well you have a very high infrastructure requirement. You either need an oven to cure it, or you have a non-automatically pre-framed autoclave, which is going to control the temperature and the pressure when you cure it. You have infusion, which is what we're focusing on. You can kind of start to see why we chose this. The material cost is still very low. We're using almost the same materials that we were using when we made a wet layout. And we can get some decent quality consistency and also good mechanical properties from this. The only disadvantage is that we do have more infrastructure required, you need vacuum pump, odd additional consumables that we do wet layout, but these are still much less expensive than an oven. So overall, you're getting a nice balance between all the various parts, a nice balance between cost and performance, which makes it a suitable candidate for us to choose. And the goal here that we want to focus on is producing an aerospace grade part using infusion. And that's relative to building a rocket, where you're spinning this thing up at a pretty high speed, it needs to be done right. Now we produce every component in our rocket with infusion, separate color there, and the structure is done with infusion. And today we're going to focus on the carbon body. This makes up the primary structure of our airframe, and as such, it's one of the things we're concerned about. The materials that we're working with are this carbon 58 and it's tubular unidimensional fiber. And you can see right, this is actually us halfway through the layout when we put everything on top of the mantle. Everything's in tubular foam still. And that's advantageous for us because it really cuts down on the layout time. What we want to do here is we want to characterize this material, take some properties from it, and simulate the fusion process. And the reason we want to simulate that is that we want to ensure that the resin will get all the way through our part before it gels, or basically turns from liquid to a gel form and have it floating. And the first test we do is a fiber reaction test, which is what you're looking at right here. So we take a small version of the preform, about 2 inches by inches, we put it in a tensile test machine, which we operate in reverse, and we record the phase. And with that, we're able to calculate fiber volume fraction, which is just the ratio of fiber total composite by volume. And we calculate that using the air, which is something we measure, the density of fibers, which is the quantity we have, and the thickness we record. And you can see here we produce this graph, and that's something we're going to do the simulation, and it's also something we do for our next test, which is a permeability test. Now, the permeability, which is really denoted by K, that's a measure of how easy it is for the resin to flow through a preform. And we go ahead and measure this quantity, we just do an infusion on a glass plate with the preform we want, and we record the resin decision over the time. And from that, we can back calculate what our permeability is. So now, with these two quantities, which are more characterization of our fiber bed and data that we've been given from the manufacturer of our resin system, we can go about actually simulating this process, which is what you're looking at right here. And this is simulated in software called CAMRTM. It's a finite element software meant for both resin transfer molding and infusion methods. And you can see resin traveling along here where it's perfect with fill. And it tells us the simulated fill time, which is the time we get all the resin in the part, it's 942 seconds. Now, it's a good idea if you can to compare this to a numerical analytical solution, which is something that we do have. And that shows that the fill time is 900 seconds. So these results have some decent agreement. They're not quite on point, but we're not too concerned about that because the gel time for the resin is 3,600 seconds, which is an hour. And this simulation shows us that we can implement this on a full-scale body tube without much problem. Now the concern for us is getting this flow front, right? We said we wanted to be able to control that, and you can see this in the simulation. It's nice tube with flow front, which is flowing along the tube. We want to actually achieve that, and our solution to that was a female ring-shaped mold, which you can see here. Well, we're focusing on the body tube here today, but there's also the nose cone, and we also do this for the couples. And this is a machine, not a CNC router, and 2 halves, and coated with polyester coating, which gives this very nice, smooth surface. And there's an inlet, and also to vacuum pump. We use spiral tubing, which is what we used before. I'm going to circle, and that way, you're hopefully going to create that circular flow. What we did after actually implementing and testing this, you can see here this last fiber couple that we're using. Yes, we did achieve that flow point. And that's very important, as that means at least in the radial direction around the actual circumference of the tube, a nice even distribution of resin. As well, this is also important, so it just shows that we can effectively implement this process when it comes to manufacturing. So up until this point, we've been talking about processing composites, and I think we want to minimize that knockdown factor. And before we get too far, we're going to actually simulate the technique and make sure that it can work. And that's what we've done. We've simulated this, we've shown it works, and now what we want to do is actually evaluate the quality of our components. And we're going to use 3 of that. These aren't the only 3, but 3 that are very relevant to us, especially in the field of rocket, dimensional accuracy, firewall interaction and the void content. I hope I don't have to explain why dimensional accuracy is that important. If you can't have dimensions, you want how are you going to integrate any of the subsystems you need? And you can see this table here summarizes what the thickness targets were, what the internal diameter targets were for this cross system. And the major punchline here is that yes, we did reach those within the tolerances we set. More importantly than that, and also that's extremely good for us, is that we've been able to couple parts. So we can see here we have no stone coupler and a body tube. We've taken these fresh out of the mold and we're able to put all of them together without any sanding or further machining operations. That's an important thing for us because sanding carbon fiber is not fun. It's not fun. It's definitely not fun for your lungs. You need a lot of safety equipment and a lot of also industrial equipment to do that. And the next thing that we're going to look at here is water interaction. And this is a bit more specific to composites. And as I said, we looked at this and it was an important quantity for us to, we actually did the simulation, but it's also an important quantity for us for both the mass of the rocket and the mechanical properties we get. So this formula here just explains in the rule of mixtures what the strength of the composite is between fibers and your resin material. And the fibers here, well, those are strong. That's what we want to maximize. And the resin here, well, that's not as strong. We need the less resin we have in there, the better. So let's say we're doing a wet layup, we're going to use carbon fiber, and we add a bunch of resin in there, we have like 30% fiber quality. Well, that in comparison to, let's say, a 60% fiber quality. That's a lot of excess resin there, which is going to add mass to our components, and it's going to slow the rocket down. And also, it's going to make it tough to reach that target. So maximizing the fiber volume fraction is extremely important. The next important thing to note here is that within the fusion process, about 55% is the max you're going to get. Past that, you might get locally, but globally, it's very difficult to get that. So we actually took some samples from the body tube, recalculated our area of wafers before it seemed a little bit high, and we calculated the fiber volume, which was between 50 and 53%. With infusion, you will have variation with the fiber volume fractionally, but this is still an extremely good result for us because this corresponds to the upper end of what we can do. And also, of course, it's a realistic value. So it's not like we came here telling you that we got 70%. That would probably be a lie. And the final thing we're looking at is void content. And voids are something you can see right here. So this is a Microsoft thing that's actually taken bodies. It's known as three things. You have the white here, your fiber tone, where you have all your filaments and carbon fiber put together. In the gray, you have the actual resin, and in the black, you have the void. And a void is just where there's no fiber and there's no recycled parts. And so how it works in the composite is that you have your resin material, and goes ahead and allows the fibers to take the shape and hold that shape. And at the same time, it also creates the load between the fibers, which really provide the strength. So if you have a void here, it's just nothing. There's nothing there to transfer the load. There's nothing there to hold the shape, and it parts. So we want to minimize that as much as possible. And to do this, we took some of these samples, put them under a microscope, and then analyzed them in an open source software called imaging. You can see right here, this is the image that I got from the microscope. Highlighted in red is the presence of voids. Now, for an aerospace component, most of the time they're going to require less than 2% void content. What we measured was 5.4. That's certainly above what we would like to be. Now, to summarize all the manufacturing results, we have hit most of the targets that we want. We have internal die thickness and fiber volume fraction all in a good spot. The only thing we missed is the void content, which was too high, as I said. So the question here is, well, is the body tube going to fit in the conditions we have, or is it still good despite that higher void content? So we took a sample tube, we put it into a compressive testing machine, and at 21,000 pounds, we had partial fit. I say partial because we kind of crushed one of the ends. We didn't have a nice square enough cut. And max range load is about 1,000 pounds of force. So despite that higher content, we're not that concerned. And overall, even though we have that, it's still up. So to conclude here, this has been a very successful project for us. First time our team in the past 4 years has produced a fully SRAD airframe. Every component here was manufactured with fusion. And we've gotten some good results out of this. It's meant that we're getting more advanced manufacturing process. High, and the next step for us is looking at process optimization in ways that we can reduce this further. So that's all I have to say today about fusion. Like I said, it was a very successful year on that side. And just before we finish up the questions here, I do want to make a couple of acknowledgments. First off, to the Neil Structures and Composite Material, particularly the questions passed out over there and there in the SRAD, and also the lab technicians in the park. All of them helped us with some advice in setting up our tests and using the equipment. it would have been impossible to get all this stuff without them. And as well, all the various costs and costs here provide us with consumables, materials, and equipment that without which I think it would have been this project. So with that, I'll open up for any questions you have. Yes. Yes. Major iteration for us, this started all the way back last year when we first tried infusion. First major iteration for us was fixing the mold. We had a previous fiberglass one which didn't have as much as we wanted. After that, the next thing we looked into was degassing and also the other thing that we changed up was basically unresident parts. It's a little difficult to explain, but more along the lines of looking at the inlet and, well, I'll just kind of do a little bit. So at the inlet here, as you can see right behind here, we have the pipe. So all of this we saw there on the part. So one of the things we did was basically opening that up, letting the person just get by, and then varying how long we need to evacuate that excess air, because we can't get any of that.
I'm more concerned to talk about anyone the results. How do you results compare?
So with wet layup, it's all over the place. We haven't really been able to find a consistent value. Usually it's noted as intermediate, so the chances are it's going to be higher than this. With pre, it's going to depend on the manufacturing or exactly how the person is. I've seen a pre-preg layup where they have 6% oil content, and then a good pre-preg layup where they got 5%. So it's really dependent a lot on the skill of your laminators and the skill of your brand, which makes it difficult to put a constant quality. It's the major note though is that if you do a wet layout right where you're mixing, you're going to air in there and just mix the resin harder, you're going to mix air in there when you light, you're definitely going to get higher. So the infusion process itself, we're not going to lower the bag pressure any more than it is, right? We're going to keep it at 1 atmosphere. And the reason for that is that we don't want to get any excess air in our part, which is what's going to be voids. The thing that we can do is vary the amount of pressure that's acting on the resin. So what we have done is in the past, we just have somebody have the atmosphere outside because it's just outside normal conditions. What we could do is put it inside of a vacuum chamber and reduce the atmosphere. The thing that we do now quite frequently is we'll let sound of a handle and kind of control how fast the resin moves, but we don't have to make it quantify how that works.
So on all of these trials we've done, can you use the same resin or something?
Yeah, we're using the same system.
Okay, so there's no, like, I don't know, you guys mix that, they're changing viscosity on any of them?
The viscosity, at least from what we've observed, is consistent. The thing that you would use to measure the viscosity is something called a thermometer. And the longer that we can have access to is just the resin that has such a low viscosity that we don't put a big on it. And then it's just like a huge mess in the lab. So in that sense, we're really just trying to help. Infrastructure. So, and so like for an actual community infusion, so the company we used was about $600 total. We have a couple $100 in tools, and then you also have an actual tool that you're using. For us, it's a little bit tough to compare because we sponsor this design team. For that reason, so you'll probably have to buy on the shelf for about $1,000 before you start looking at specific. And tooling is also going to depend on what you're working with, and that's are you going to use a metal tool or are you going to use a wrench shaped tool? Are you going to have a modeling where maybe you're going to use steel, N-bar, there's all kinds of tools out there that also has a lot of over the course of this year, I've been around 20 different quite a lot. Yeah, that's actually what results a bit in the pressure gradient of the part, actually back side on that. So you can see the amount of pressure acting on the resin is actually vary. This is actual solution versus law, which covers that previous analytic solution we were talking about. And because of that, you do have thickness variation cycle.
That's just thickness variation, you also get variation in voids
Variation in voids, I haven't thought about quantifying that. This variation is really fiber bond variation instead of the result of that.
You're asking the sample going to agree on the outside, you will because what causes that is you've heard of the gravity device, it's nice strong fit, that ridge that causes minimum area.
Yeah.
Something that manufacturing process is something.
So you're talking about that little side of the line.
Yeah.
Yeah, so that's actually the party line of the mold. And because we manufacture different size, you can't perfectly, I mean, especially with the 3-axis space scenario, you're never going to be perfect. This is a tight enough fit what our purposes are, and it's not quite as pronounced as it is on the box actually. You can definitely sand it around. Yeah. Yeah, we can sand it. And the other thing is that you're right, it does kind of produce air gaps, and that was an issue with the mechanism. Because we were able to produce parts much earlier this year, largely because we organized ourselves better during the summer, we were able to go ahead and fix the problem we had there and make our business go forward. So despite that, it's not really a concern. Yes. So at this point, the thing we'll be looking into is, so the two things to look into would be void content. One of the ways we can look at it is resin degassing. So this is something more eyeball, but we haven't really looked into the effect of how often we degas. Base gas in here, so looking at, it's just you put the pot of resin inside of the vacuum, turn on the vacuum, and remove all that extract. So perhaps that's moving this longer so you can remove it. The other thing is there's actually relationships that govern the void content and flow rate. And that's where that varied pressure might actually be quite useful of us going ahead with a control system that can control the resin flow rate by altering the pressure. Yes. The biggest challenge is the mold, for sure. That is nice to get. Third time.
Does that work? Okay, it works. Might I ask you to move over that side, because apparently we can only change the slides from tools from the laptop. So if you like to be in front of us while we present, please change your place.
Yeah, he said he'd like us.
So we can hear you see it.
I don't want to see it. He said that he doesn't have to use it.
Right, I guess we can begin. I welcome you to our presentation about risk-constrained dynamic probe, and we use that for controlling our air brake system. So we are from Switzerland. We are the team from Zurich. We are called TEL, and I am Johnny. This is Fabian. We will be presenting our team. Let me start an overview of the presentation. So we start just with the basics of the whole idea. Then we go into a design overview, what is contributing to the system, what is the algorithm behind it, what empowers our control, and finally a short insight into our testing, and then we're already at the conclusion. So let's start. This is really tedious. Yeah, let's start with the concept of our braking algorithm. So the idea is that we have a motor that is too large, such that we shoot target apogee in the nominal case, but also in any real case, independent of the disturbances we encounter, like a stronger motor or anything. So we overshoot in any case, and afterward we assess the state of the rocket and induce a braking phase such that we get to the right apogee. This concept is not easy. There is only one attempt, so reliability is key, and we don't have too much time for development, so we like to keep it simple. How this is done, I will show you right now. So here we have the system overview. There is my few old slides. Yeah. Maybe give me a second to change to the correct version slides, because we might really miss content. I'm sorry for this incident. Right back with you. All right. So, what do we need for our control system? The first thing is we need the sensors provided by the avionics system, which most importantly are velocity of the rocket, synthesized from readings from the IMU, the gyroscope, and the barometer. These are put together with a state estimation, and the current is then fed into the control algorithm, delivering a control signal that accurately defines how much the air brake system needs to be extended to get us to the correct apogee. This control signal is then given to the motor controller that actuates the motor such that the plates are extended correctly. So, a closer look at the design. We can see that air brake plates are perpendicular to the longitudinal axis, thus also the direction of flight, and they can be extended in horizontal direction, thus increasing the the effective surface area of the rocket. I'm going to go into the parts contributing to the system now. So most importantly, we have linear guides provided from Schneeberger. And at this point, I'd like to mention that this is due to our great structures team that we managed to build such a system. So what guides provide is a smooth linear motion, and they have a low friction coefficient. So if you take a look at the forces that are attacking the system, we have on the right the drag force put laid down, and any other conventional air brake system, you see those flaps. In that case, the actuator is actually working against the drag force. The drag force is consumed by linear guides, and the only force the actuator has to provide is the force counteracting the resulting friction. Right, I need to speed up a bit. So here we have the air brake plates. We've seen them before. They are attached directly on top of the linear guides. And if you add a set of gears and an actuator, you can move the whole system finally. All right, so now we're getting to the interesting part, and I give the mic to Fabio.
Yeah, before Johnny described that we would start controlling at burnout. Now I would like to explain why we chose to only start controlling at burnout. That's because in order to do effective control, you need to have a good hit of the apogee of the rocket. And the estimate gets better the closer you get to the apogee, of course. And most of the inaccuracies come from the motor. So if we did some wrong braking before a burnout, braking too much, we could lose too much velocity and be unable to reach apogee. So we had to only brake after burnout. Then also the effectiveness of brakes is directly proportional to the square of the velocity. So it's most effective at high velocities, which is directly after burnout. So afterwards, in this coasting phase of the rocket, there are two main parameters describing the flight of the rocket. It's the altitude and the weight. The pitch of the rocket is constant for most of the coasting phase, except for the 2 to 3 seconds where the rocket starts turning, so we can completely leave out rotations. This simplifies the system, so we only have 2 dimensions on which we can do the control. Yeah, the optimal control allows us to minimize of missing apogee. So either not braking it, not having the brake potential to be able to brake later into the flight, or braking too much and undershooting the apogee. So using optimal control, try to always keep the current apogee estimation a little bit above apogee and just close the gap in the end. Now I'd like to give you a little into the algorithm itself and how it works. So first we'll have the 2 dimensions, velocity and altitude, and how they are used to define the state space. The state space needs to be discretized, so you can run a dynamic programming algorithm. And after discretizing it, we need a cost function to optimize. This cost function should be optimized such that the risk is minimal of missing apogee. And then I'll show you how to run the algorithm on there. Here you can see the target trajectory that we reach. So in the dashed line you can see the burning phase in which we don't do control. So we will ignore that for the further graphs. And afterwards you have it following the trajectory which exactly reaches apogee as we wanted. You can do the target trajectory again in black now, and you have to do the trajectory that has the, if you were to start with the velocity where you can still reach apogee, that trajectory is shown in red. So at this velocity you would have to brake the entire flight to just reach apogee. There's another trajectory where you have to leave the brake the entire flight just to make it to apogee. That's the green. Both of these are found by simply integrating the dynamics backwards from the target position, once with full brakes and once with brakes. If the rocket ever has a velocity above the red line, the control is really easy. You just have to brake as possible because you're not going to reach apogee anyway. And if you're below the line, you just shouldn't brake. These two areas are what we define as critical zone, and they are an ending state for the DP algorithm that I'm showing. So once you get in there, there's no need to calculate what to do anymore. Now we need to discretize the grid in order discretize the control space in order to run the algorithm on it. And common approach is to just put a grid over everything. But as you can see, most of the grid not even in the control space, so it's rather inefficient. So what we have done in that instead is to warp the grid. So we have a grid that fits exactly into these two lines. In order to implement it, we had to keep in mind that the lines are not parallel and there are no right angles. So the rectangles actually have to be stored as multiple line segments. You can see that should the process in order to accurately calculate where the trajectory ends. Now that we have the grid, we can actually simulate the dynamics. For every point in the grid, shown as x, it is defined by velocity. There are different possible air brake inputs. Here we have U1 that goes up, that's if you don't brake, and U if you brake fully. Additionally to the air brake input, changing the trajectory, there's also a noise introduced by the wind or aerodynamic uncertainties. And this noise is modeled as a Gaussian noise here. And usually you would simulate that using one model. But what we do instead is we split the process into two parts. First, we calculate the expected value, the center value, and then we just apply a Gaussian fit to the entire grid, to every space at the same time. So now we need to define a cost function, which we can optimize in the end to find the best control. So first off, we want to reach apogee. So this cost function is pretty straightforward. We just have a cost of 1 if we miss the apogee, if we get into the critical zone, and the cost of 0 if we hit it perfectly. Additionally, there is a physical cost on the air brakes, because the air brakes have a limited movement speed. So we have another cost that's directly proportional to the movement of the air brakes between two states. Each of these costs has a factor that will be optimized in the end using binary. So now that we have the cost function and the dynamics discrete, we can actually run the DP algorithm from bottom up. So we start from the back and make our way to the beginning. So what you can see here, state directly before apogee, and there are different air brake values, and the algorithm tries to minimize the cost, so it chooses directly at apogee, which has the lowest cost. Keep in mind, due to the blurring, even values that are just close to apogee are better than the ones that are far away. Once we have done that for all the points that are near, we can repeat the same process for the points that are a little bit further back, because we now know the cost for every point. For every point, we just store the cost and the optimal control value. What you'll see here is that points that follow the target trajectory that we defined at the beginning go through the center. They will always choose the center brake, so they will always brake 0.5. The brakes will stay half-bended. But if the rocket turns out to be faster than expected, of course, extend more. But thanks to having the cost function that's also on air brake movement, they won't just change to as soon as we go a little bit above. Just by balancing these two costs, you can get a smoother function. I'll show you that now in an example of the results. Here you see the airbag value that was calculated. White means full braking and black means no braking. As you see, the target trajectory shown before follows the gray line. Yeah, and we found this, we had to choose the two weights for the costs. And those we chose by binary search, just by looking at all parts and seeing how fast the airbags move. And if there's any path where the airbags move too fast, we know we have to adjust the factors until the airbags move slow enough that it's physically trackable. And at this point, we leave all of the remaining weight pretty much to the optimizing apogee.
Alright, so let's get to the final part of the presentation, which is testing. So what we did so far is a number of ground tests, seeing that the mechanic system itself moves smoothly and that the electronic system behind does its job. Further, we tested the control software within a simulated environment in MATLAB, which allows seeing if, given the input, it delivers the correct output. At this point, thanks a lot to some guys of the other Swiss team from the EPFL, which with them Hassan, who wrote the whole code we use now. So the last and most important test was the rocket into a wind tunnel, which looked more or less like this. No, too much. And what we figured out there is that the values calculated for the drag force created by the braking surfaces we use are pretty closely by the values measured in the wind tunnel, up to 80 meters per second. Everything else we'll have to see at a launch. So, yeah, with that, I'd like to conclude this presentation. I would like to invite you to our we're launching on Thursday, 9 to 10, about. And for your pleasure, you can see here the final implementation, moving a bit, and if you have any questions, please fire away.
Go ahead. Yes? That was just from simulations. Well, we've seen from previous launches that this can vary, like the motor performance can vary by like %. So this is the kind of error we are expecting, and this is also the kind of error we are able to compensate with our output of the motor. Yes, as long as it's not more than that. I think he has a question.
So I have a question about the real-time implementation of your controller. So it looks like you're starting from your final altitude and back at some time, like value. When you implement this in real time, how have you determined how expensive the computation would take some of the terminal times that we go back and
Yeah, I forgot to mention that. This is the nicest algorithm. We run all of the value iteration offline, and then we have the table that I showed at the end, the black and white image that is stored on a microcontroller, and all the microcontroller has to do is measure velocity and altitude and look it up on the table. Yeah, like once
velocity for about 310 meters per second. And at that speed, you would expect about 180 newtons per blade. So the bending moments, not the numbers in mind, but it's about 5 centimeters times that force easily taken by the linear guides. Yeah, more questions? Go ahead.
Yeah, we tried it out before, but and we've seen from previous launches that simply integrating the IMU, while it was actually good enough to just use the IMU as well as possible, and for that we're using simplest. So the carbon filter is definitely planned for the future, but for the ones we tried, we always had some bias because the barometer is biased at high wind speeds, which has lower pressure inside the rocket. Yeah, it's not common. Well, with this controller we can guarantee the risk of which we can calculate it using a similar method as the GP and actually assure that we minimize the risk of not hitting apogee. While with the PID, we wouldn't really know how to guarantee that. And it's all in the simulations, like when we discretize the dynamics, there we take the air density of the altitude in account to find out how effective the eggs are at this altitude and how much we have to extend them to get the expected force. In this case, we really just have to plug the velocity and altitude into the lookup table. So technically it might be a little bit faster than the PID, but seeing that we only have to do it 50 times a second, we could also do a PID at the same time.
Okay, the airings are based on what it's called, the dot-com method for the drag calculation, and then we have an extended Barrowman method for the calculation of the center of pressure. Basically, it's analytical. We're talking into CFD, but figured out that it's hard to integrate low speed and high speed, because we have the verified results for low speed. We have no idea what happens around 300 meters per second. Yeah, because we didn't do any high altitude flights. Yes?
So I'm just curious about how stability of the economic sense of I guess I think you should figure exactly the technical conditions, but how stability change for example, the formation of the
That's the advantage of using air brakes instead of, for example, canards. Because what air brakes do is they shift the pressure backwards, which means that we actually increase stability. As long as we don't have too strong side winds, that's all right. Actual extension changes the center of pressure by about 5 centi, I believe, because they are located close to the center of pressure already. Any questions? Right.
Maybe. Oh, there it is. Okay, so my name is Eric. This is Colin Ashland. We're with Colorado State University's rocket team. We're going to talk the design of the Ares 4 liquid propellant rocket engine. So a little bit about the history of CSU at our competition. First years of competition, they designed a hybrid motor. The first year used nitrous oxide and HTPB, hydroxyturnate polybutadiene. And the year after, they sought to improve the same engine, and it was a very similar design, but they used HTPB, nitrous oxide, aluminum, and wax instead. Oh, and I forgot to the first year team won the Gilmore Technology Award for the work they did. The year after that, last year, the team decided to switch and try out doing a liquid propellant engine for the first time. They were the first liquid propellant engine to ever successfully launch off the pad at the IRA competition. This year, we have planned to improve the propellant engine design. This is just a video of the two hybrid motor static test flight. Because there's no sound on the videos today, but this next year this is the last liquid propellant engine, the first liquid propellant CSU had attempted. And next, unfortunately, although it was the first to successfully leave the launch pad, it blew up at 500 feet. And later on in the presentation, we'll get into why we think that occurred. But this mission was to improve upon last year's Ares 3 liquid propellant rocket motor design in the SRAD 2,000-foot category at the IRA competition. To do this, intended to separate the propellant tanks in the combustion chamber, redesign the injector to a pintle style for more efficient mixing, and develop a model to predict specifications of our engine more accurately. This involved making a scale motor to optimize our design, which would eventually lead into our full-scale design. Also creating two different programs, one that would analyze the trajectory of the rod itself, and one that would predict accurate measurements in the motor, such as thrust, combustion chamber, pressures, all sorts of stuff like that. So this is a CAD model of our current design. We start propellant tanks here. We have nitrous oxide as our oxidizer on the outside tank. We have ethanol fuel in the center tank. These are pressurized to 700 psi, and that's the relief valve that is mounted to that top bulkhead, although it's not included in the CAD diagram. The nitrous oxide is self-pressurizing just to the temperature at which it vaporizes at. It's also used to run the pressure of the ethanol tank through the help of a groove seen in this diagram and that piston. So when we're ready to fluid flow of propellant into the combustion chamber, we send it through this custom plumbing into our injector, where it's mixed and enters the combustion chamber, and it's like a preheater sitting right there at the top of the combustion chamber, and the expanding gases are accelerated through the throat of a phenolic insulated nozzle, which you see there. And the last component of the combustion chamber is in the HTPB liner, which although it does aid in ignition and helps maintain combustion of the propellants early on in ignition, it acts as a thermal liner. It ablates away heat, goes through the nozzle, and keeps our combustion chamber tube from melting. So the relations we made between last year's motor and our current motor design is first in severing the propellant tanks from the combustion chamber. So I mentioned we talk about why last year's engine blew up when it did. What we think happened is, if you see this as last year's CAD drawing, the propellant tank and combustion chamber was all the same, one continuous piece. So you can see how close we have fuel, oxidizer, and a combustion chamber, all the flames going on. So what we think happened is a tube that is to initiate ignition of the fluid of the liquid propellants was getting pushed out the nozzle, constricted the flow of the nozzle enough that the pressure in the combustion chamber exceeded that of the propellant tanks. So propellant got pushed into the propellant tanks. We didn't have to go far, only maybe 2 inches to go through the injector and be in the propellant tanks. Eventually, enough of the expanded gases left the nozzle, and now the propellant tank had pressure, then the combustion chamber, pogo occurred, and oscillations drove the propellant back and forth until it tore the rocket apart. This would make sense because it didn't blow up on trail, it blew up at 500 feet. It took a while to get to that point, but separating the combustion chamber and the propellant tanks will effectively dampen the system, ensure that resonance isn't reached between you, and if there is blowback, it would have to travel over a whole foot to be in the tanks rather than 1.5 inches, 2 inches. Although separating the combustion chamber and the propellant tanks came with benefits, it also came with some added complexity. We needed to find a way to deliver propellants from the propellant tanks to the chamber. So our solution was in these custom slide check valves that we've developed. I'm not sure showing up very well in red, but this is it in the closed position. This is it in the open position. So you can see with these red lines, the propellant allowed to enter, leave through 4 radial holes, and fill up a small chamber between a static sleeve and dynamic sleeve. And when the slider in that position with an actuator, which you can see in these pictures, it's constrained and the fluid cannot flow. But as soon as we blow a pyrobolt, which is this guy here, a nylon bolt that's filled with a powdered charge, so we blow the powdered charge and it cracks, the static or the dynamic slider slides down, the slide check valve is now in position, and fluid is allowed to pass through. It connects the circuit of fluid flow, if you will. It's worth noting this entire engine was all manufactured by hand by people on the Colorado State University team. None of it was bought. And after the propellant leaves the combustion chamber, it enters the topmost portion. After it leaves the slide check valve, enters the topmost portion of the combustion chamber. This is our 3rd big design innovation this year. We went with a pintle style injector. So this is a diagram of it here. The ethanol fuel travels through in the path of this line in the center of the pintle and leaves out of 6 radial mounted holes. You can see a picture of us spraying water through it, and that's how it gets injected into the combustion chamber. The blue line here is the line of nitrous oxide, where right before it enters the combustion chamber, it impinges on the flow of the ethanol. And that's going to help ensure very efficient mixing. This is a video of the small-scale test fire. So a small-scale prototype of the full-scale motor that we've designed. So that's the preheater off. Liquid nitrous oxide and ethanol combusting. Moment of hybrid burn mode where we ran out of ethanol, we had nitrous oxide with HTPB liner in the combustion chamber. As I just kind of said in the video, this is a picture of the full combustion of nitrous oxide and ethanol. Get the nice shock diamonds. This is the hybrid burn mode that we get from the HTPB liner after that. Here's Colin.
So we learned a lot from the small scale, and one of the most important things is that we got like a nice reliable thrust curve. It was replicated half times. And so with this thrust curve, I used the trajectory code for to basically run a couple thousand simulations of rockets that are scaled up by a thrust factor, which uses the amplitude of the thrust curve, and a time factor, which increases the duration of the thrust curve. From this, we designed and that would be most optimal to take the Ares floor to about 11,000 feet. Reason being, at the time we were using a control system, we're planning a control system like what the previous presenters mentioned to up to exactly 10,000 feet, so we wanted to overshoot. So what could go wrong, right? Yes, so you'll see it's in slow motion. You see it's very similar line to, yeah. Very designed to full scale. Really, just the propellant tank is larger. Also, the combustion is slightly longer because of the increased throat area. So preheater's burning, about to go into slow motion. A innocent moth will go towards the flame, and then something will happen. I don't know what. So there it is. Yeah. So what we learned from this was that we probably pumped too much mass flow into the combustion chamber. And the issue is ethanol can combust very easily, but too much of it built up before combustion even began. So once it began, though, it happened as fast as it can, and it was too much for the combustion chamber to take. So we got together with the team and we said, hey, I'm not sure if we can take this very heavy rocket to 11,000 feet. Let's try cutting weight wherever we can. Let's possibly use gravity controls, and yeah. And so we redesigned the engine that the mass flow was significantly less and the propellant tanks was significantly less. And so, yeah. And so this is built from the full scale, from the new full scale. Making ragdoll out of that plywood piece there. And, yeah, so we got a good burn now. So you can see we still have this strange oscillation in the pressure chamber. So if you see nitrous tank is the blue, the ethanol is the orange, and those act like fairly, reliable. But then predictably, but then the combustion chamber acts very haywire at the beginning, and that's the same hard start that we experienced in the explosion. But because we have significantly less mass flow, it wasn't enough to float our whole system. We also experienced a bit of combustion stability, but the combustion instability is far and away lower the pressure of the propellant tanks, so we don't have to worry about blowback and poking due to the separation of tanks. So we did mathematical modeling of the system, and as you can see, we were able to determine C at every moment, the thrust coefficient at every moment, and a very important factor called the thrust coefficient. So we modeled the entire system as flow exiting the orifice. For the ethanol and the nitrous, we were able to do this because we had pressure transducers for both. And you can see we have a fairly reliable for the behavior of the discharge coefficient, which is very useful in the development of a thermodynamic model that was created in order to predict the flow characteristics and the chamber characteristics. So by implementing the injector design, the propellant volume design, and the densities and everything of the ethanol and nitrous, as well as the geometry of the nozzle, one can converge to a steady state solution of how the combustion chamber will form and the mass flow that it will generate. A step further that we took was by calculating the heat loss through the vaporization caused by the expansion of, essentially by the loss of the ethanol and the nitrous oxide, and also the heat loss due to the expansion out of the side check valves. So on the top here, you can see the blue line is the actual performance of the actual pressure measured in the propellant tank, and in the yellow, where the orange is the predicted. And so there's essentially two phases of nitrous expansion, and that's this phase to begin with that ends a little after 7 seconds, and then the vapor phase where it kind of, almost ideal gas laws depletion. And so the code that was generated was not able to do the vapor expansion, but that's not too important because the vapor produces much thrust, so it wasn't a priority. So it stops calculating at the liquid, and you can see it runs out at the exact time that the liquid comes out, so it's a fairly good predictor, even though it doesn't fully align. On the other hand, the combustion is a fairly accurate linear interpretation of the combustion chamber pressure, but we are unable to predict the train startup phase as well as the oscillations that occur in the middle of it. So, yeah, there, as I mentioned before, there is some combustion instability, and by doing Fourier transform on it, we found that it's approximately around the 140 hertz region, which is the same hertz that the explosion happened on the Ares 3 last year. The only difference is that it doesn't increase in amplitude with time. It, the average of it stays more or less decreasing. So due to separation of the tanks. Here's just a couple of figures for our full-scale engine. We are expecting a total impulse around 4 pound-seconds. We are achieving C-star efficiency near 90%, and we will produce an average thrust around 500 pounds. Another important factor for the propulsion team is that we did this with a fairly low budget. We were allocated about $5,000, of which we spent about $4 on parts, tools, disposables, consumables. Yeah. So yeah, we certainly learned a lot from this year. We are, you know, if we had infinite time and infinite funds, we'd produce much better product. But the main things that we would bring to next year would be to find all the failure modes that we were able to discover, and in bringing, you know, the young ones into the shop to, you know, understand how we make these parts and you know, good engine or good machining practices. We would definitely encourage them to get started on this as soon as possible, because, you know, if you blow up an engine a month before competition, your knees are going to really hurt. So get all this testing in, you know, early on. So we would like to have more members on the propulsion team. We had basically 3 dedicated members on the team. We had help from other members, but, you know, the bulk of the load was, you know, fairly tightly bound. With all of the fluid dynamics and the rocket trajectory analysis that we've done, it would be fairly easy to scale this up to get to 30,000 feet. And so I think that should be the goal for next year. And begin experimenting with different propellants. Certainly kerosene, as the fuel is much more, you know, specific impulse, better performance with it, and changing the fuel is less cumbersome than changing the oxidizer. But liquid oxygen should be begun to be considered because it does have such better performance. And lastly, I think going for a full-scale test fire, rocket test fire for competition would be, you know, tremendously helpful. So, thanks.
You know, we looked at a couple different styles of injectors, and to be honest, with time and money, the highest constraints, we found something that worked well and stuck with it. But one of the others is nitrous oxide vaporizes so readily that as soon as it's injected out, it's vaporized anyways. And we've found that the position of holes and things affects the mixing and efficiency of the burn than maybe we would have thought of otherwise.
New can of worms. We do actually have a cone that directs the flow more toward towards the nozzle there. You can see, yeah. So that does in some part do it. And then as far as machining goes, we machine one fitting that the pintle is able to thread into, and then the pintle itself takes maybe an hour and a half to machine. So it, you know, buying, I don't know, $1 worth of stock, we get $20 worth and make 20 pintles. It's obviously a lot more cost effective. We don't have much of a budget, so. We measured pressure drop from the propellant tank to the injector, and that's actually what the, well, I guess we measure of the combustion chamber, and then, yeah, before then. It would be nice to measure pressure of each individual component. The only issue was when we had 3 transistors. Yeah, and not to mention transfer with the DAC, which we also wanted to their temperature at different locations. So certainly a lot more to be done with the system, but yeah. Yes, please. Yeah.
It's not included in the diagram here, but you can see work for it in this bottom bulkhead. Right here, and we actually went through a couple different design iterations, but after messing with the actuator, which we had talked about, and finding how reliable we could make pyros, we ended up making an attachment that screws into there with a check valve to allow only one flow into the propellant tanks. And it has a fitting with a male and female end that is attached into place with 2 pyro bolts. And so after we fill and we back off from the rocket, we're getting ready to fire. The first thing we do before we light anything else is we blow the pyro bolts. And so when those broke, when they break, the 700 die in the fill line. Definitely true.
We've had 3 burns on this current design. And another reason to change to the multi-tank design is the machinability of an enormous piece of tube is I mean, it's difficult to fit on and everything like that. So breaking it up into 2 components certainly reduced the length. And last year, I believe, had, what, 4 or 5 success burns with its full scale. Yeah, so, and then it blew up twice before, blew up once before, and then once at competition, so.
Also, we're seeing similar, the big thing is when we start, we get a hard start, and we see a fairly large pressure spike. And we obviously hydrostatic pressure test all this stuff, make sure it has at least a 1.5, in fact, over that safety factor to it. But if we were on the first configuration we had chosen, based on the program we had written out, spit out all those numbers, C star and L star, and what we need was telling us we were within our range, but we could adjust that program some, and we had a pressure spike that was higher, significantly higher than the load that had been picked up. And I mean, not that it would have been good anyways, because it blew up and totally destroyed the load cell anyways. But after redesigning and looking at that code again, we decided to keep our pressure to it. It's about 190, 180, 190 is where it averages out, but the pressure spike still gets maybe 700, 800 right at the beginning. That being said, that's well within the range of our combustion chamber, like the actual wall of the combustion chamber itself.
So before even doing that, we simulated the original design, and yeah, that was just to really get the line of the liquid nitrous running out at the same time as the ethanol, because that's where the majority of our impulse comes from. But it said, I can't really predict the transients from that model. But you can predict the mass flow and which is really the most important. So it was about 30 inches for this new one. We had it at 60 inches for the original one that blew up. That was another change we wanted to make. Not only does it reduce the width of the combustion chamber, but if propellant's building up, it gives it less room to build up.
Thank you very much.
It's kind of terrifying. This is the first time I've looked at the I should make some They're going to be a channel or is You can make that. You should make that as soon as they still can do it. But they should be but they're not good, they can go with the parachute, get all sorts of go with the parachute,
so maybe we can start. So hello everyone, my name is Balazs and I'm presenting AGA Space Systems Student Society. We have 2 rockets here, and we actually a team from Poland, from Europe, and we are a sole team in our country. And actually, this year is the first time any team from our country is present on the competition. So I think it'll take like 2 minutes to introduce Poland to you, introduce our student society, so you will have the better picture of what we do, on what the Poland is in the space industry. Yeah, as I said, we come from Poland, and we have many achievements in the space industry, but recently it is rapidly growing. Since 2012, we are a member of European Space Agency, and in 2014, the Polish Space Agency was established. Its main task is to cooperate with the private sector, because that is the commercial market is like the focus in Poland right now. And yeah, we then have like a few achievements. So for you, specialization that Poland is developing right now, the projects that we do is most likely space robotics, downstream technologies, so Earth observation and some using of satellite data, and yeah, some space propulsion, and the propulsion of hydrogen peroxide developed in Poland is very unique propellant, and it is high concentration, so it is very promising technology. So it are the fields that are thriving in Poland right now. Yeah, and we also want to contribute to space industry, not only but maybe worldwide. So since 2013, as we were settled, 6 people started this student society. So we are very young, and then we have built rockets, space balloons, and constant probes, the planetary rovers. We have some achievements in propulsion, in liquid propulsion, hybrid propulsion. So our like a very first achievement that started this whole student society is the Council Planetary Probe. We won the competition in 2015. We defeated, we won over like maybe 80-90 teams all over. It was organized by NASA. So a good kickoff for the student society. We also won the Global Space Balloon Challenge with our space balloon design. And yes, since our beginnings with propulsion, with rocket propulsion, we since 2015 we have built 5 rockets. Few of them are still in development. We have them here, so we are here, as I said, with 2 rockets.
And we started our origins are with hybrid propulsion, but since like 2 years we are developing the rich propulsion, and we are using nitrous oxide as our oxidizer because ease of handling, and we have great experience with free propulsion, so we adapted the same in the propulsion. So yeah, last year we developed we call the first rocket scale bi-liquid engine in Poland, because of course there are many laboratory scaled engines, but none of them was used to propel the rocket. So this is something we can brag about, and yeah, and this is some example of the measurements that we did with this design. The design of the feeding of the propellants to the combustion chamber, that we used the nitrous oxide self-pressurization, and at the same time we use nitrogen to pressurize the to push the fuel into the combustion chamber. These are two different behaviors. So you can see very different behavior on the curves of the pressure here. Of course, this aggregated the test was badly configured, so we dropped too much of nitrous oxide in too little time, so the pressure drop in the vessel was too large. But it shows the problem of coupling the balloon system of the fuel with the vapor pressurization of the nitrous oxide. And this is the visual result of that. The ignition was successful, and the burn was alright for like a couple of seconds, but then the pressure drop in the oxidizer contributed to a mixture ratio shift, and it can be seen that more and more fuel is burned with less and less oxidizer. So basing on that experience, we started a new project, and wanted to adapt it to rules and requirements of the area competition. So this competition is like a milestone for us. So of course we want to be here, but also we target for some greater goal. So being here is a milestone for us. We will be also with this rocket, I hope, next year. This design takes some conclusions from previous iterations, and we developed, let's say, a unique pressure-fed cycle. This is like maybe exactly the same that was the previous presentation. Very similar design when we used the nitrous oxide also to pressurize the fuel. So we have some sort of unique pressure vessel design. For bi-liquid engine, we only have one pressure vessel, and on the left side you can see the pressure curve of the nitrous oxide inside the tank, and this is from the real test that we measured it by ourselves. But in a good condition, we can draw like a 90% of nitrous oxide in liquid, in let's say 90% of 90% of nitrous oxide by liquid, with only 10% of pressure drop, because the pressure, of course, of nitrous will drop significantly due to boiling and precipitation. So yeah, we can use that phenomena to pressurize also the fuel. So this is just a diagram of our pressure vessel. We have piston inside that pressurizes, that pushes the fuel out of the tank. And we did some modeling of this behavior of drawing the nitrous oxide from the pressure vessel. We are still working on it to adapt it to two propellants instead of only one, but the difference will be that there will be some higher pressure drop of nitrous oxide, because it have to boil some more mass to pressurize to this fuel propellant. So this is just a example CAD design of our pressure vessel. So you can see here a piston that is so you can see here a piston that travels along the axis, and two conduits that also works as rails, and we use this conduit, this one, to here's fuel and here's nitrous oxide. There is combustion chamber and feed system, and we use these grooves within this conduit to push the fuel internally, so we do not have to run anything outside the pressure vessel. And what is more, second rail is a service conduit, so we can here's our avionics and go with cables and everything that we want to the system, and we don't have to bring the cables from side of the rocket. What is more, one may ask why we don't use, for example, this rubber, I don't know, balloon or something like that is used in extrusion. Well, that is one option, but this piston gives us another feature that is very important for us, and that the way to measure the mass flow into the chamber. Namely, we have here in this service bit the magnetometers, and here on the pistons a magnet, and we can measure precisely the position of this piston. So actually we can measure how much it travels, so how much was expelled from the vessel. Let's see here some trade-off analysis of these feed system cycles. For me, it's like having external gas with nitrous oxides, just wasting this self-recirculation feature. Of course, for bi-liquid rocket engines and using blowdown, we don't have control over the pressure drop ratio, so there is some OF shift, of course, and there is some high pressure drop throughout the burn. So the advantage is, of course, simplicity, low weight, but I think the like a middle ground is the self-pressurized both propellants, and there's more consistent, but of course we have constant pressure drop ratio. The pressure of both the fuel and the nitrous oxide, at least in the pressure vessel, is the same. And yeah, we fabricated few prototypes, because for this rocket here, for our rocket on this IRA competition, we designed a smaller version of the rocket and the propellant, I mean the propulsion system. And this is the prototype of the smaller version. It was tested and it works. You can see here this piece. It's very similar to this diagram I just showed you. It has three entrances from both sides, and here you can see the cables that are pushed through service conduit. And yeah, we have this larger version here with us, so you can come to our stand and talk about some more details. And this all is still in preliminary state. We did cold flows, and it works pretty nice. I mean, on this version, this larger version is still waiting. We sadly won't attempt to launch this year, but this was a hard decision. We wanted to make it 100% ready for this year. So I hope next year we will have a chance to be here and present this project with perfected state. Yeah, so that will be it, and as we say, see you in space. If you have any questions. The other way around. So if we put it other way around, we cannot show the upper propellant, I mean the oxidizer, the same way, because it will be vapor up, right? So basically that's why, yeah. Yeah, so I think that's it. Thank you very much.
About the control system. And the system for that, and that night I saw some questions. They generate the table. You have, right?
Or you can do something.
Nice. Then you need a bunch of tests. I don't know. It's cold. Don't look at that list. That was. You have to look at this and get that's just a bunch of abstracts. Are they the team that really test it down, or that's, yeah. I did call them things. Oh my God. But they only have to carry that by hand. Nice. It'd be really nice. Someday we'll be there. Yeah. Unless like
If you're gonna do it, aerosol, okay. Generate shockwaves, right, front. Behind the shockwave, that's where it is. Oh, you're flying inside the shockwave. Wild. Yeah, no, that's quite
Oh, right, it's like Michigan. So Michigan is going to work with this. Michigan is also wow, I didn't see that. Yeah. It's just the biggest 98 million flash processor and a mid-diameter body tube. Pretty much. You can do that. But what we should do is we should just nose cone fit around the case of the screw it into the top of the casing. Yeah, we need a parachute somehow. Okay. Better thing, make one section of minimum diameter body tube and with fins and nose cones, shot cord just between the nose cone and the top of the motor case. Parachute there. And what we do is we just blow the motor out the bottom of the rocket. What we want for the shape.
You just have rocket.